Okay, let's get started. So, today we're going to be talking about the surface area of a graph of revolution. So, this is section 8.2. So, what is this about? Suppose we have a graph like this from A to B. This is our function, okay? And we're going to rotate this around the x-axis. So I'm going to do an arrow like this to indicate the direction we're rotating it around. Later, we'll do it around the y-axis as normal. Okay. And if we do this, what you should be able to visualize is that we're going to get some kind of a cylindrical type thing, right? And this graph here is a one-dimensional line. So if we rotate it around, it's going to form a kind of a two-dimensional surface, like a rotationally invariant two-dimensional surface. Yeah. If we had a graph like this, for example, then it'll form some kind of a bowl. Yeah. Yeah. And what we're going to try and do, what we're going to succeed to do, is we're going to find the surface area of this two-dimensional thing that we obtained by rotating around. Okay? Yeah. So that's the surface area of the graph of revolution. Yeah, or the surface of revolution, perhaps. But yeah, graph surface. So, as previously, it's going to come down to having some explicit formula and simply calculating with the formula. Yeah? There's actually going to be two formulas because we're going to learn to rotate this around the y-axis as well. And we could either do this by writing a function from the y-axis, so writing x as a function of y, and then it comes down to the same formula. Or there's instances where it's better not to do that, and we simply have a different formula where we keep y as a function of x and rotate around the y-axis. Yeah? So these formulas look very similar, but they mean completely different things. And we're gonna figure out what these formulas are. The same strategy we talked about last time. We're gonna look at things in a very simple case where the function is linear, and we're gonna get the formula for that. And then we're going to cut things up into little pieces, put them together, pass the limit, find a formula that's an integral, and that'll give us the precise expression. Okay? So if you are comfortable with the way that we did this explanation for the arc length, what we're about to do is extremely similar. Yeah, the procedure is extremely similar. The formula we get out is going to be different. Obviously, it's calculating a different thing, but the way we're going to understand it is extremely similar. And as before, it is very important that you actually have some understanding why this is the right formula, and don't simply believe me, don't just memorize it, don't just put it down in a cheat sheet and then bring it back up. It's way more important you have some idea why it's true than actually applying it. Okay, so let's begin. If we have the simplest circumstance, so suppose we just have a function that's just constant, like this, from A to B, and suppose the constant value is L, then the surface of revolution is what? If we rotate this around, we're just going to get a cylinder. I'm going to try and draw it. Yeah? So what would you expect the surface area of this cylinder to actually be? What would you expect it to be? All right, so let's visualize this. Let me take a sheet of paper. There we go. Let's visualize this. So this is what we get when we take the surface of revolution. It's a cylinder like this. Yeah? Can you see that? Yeah. And what does it correspond to? Well, this thing is going to be the thickness, right? This will be the thickness right here. which will be b minus a. And then we have the circumference. Yeah? So the total surface area will be how high this is, yeah, which is b minus a, times the circumference around the base of the cylinder, right? And as you can see from this picture, right, the radius of the base is just L. So the circumference is 2 pi times L. Yeah? So if I take this cylinder we get and just unwrap it, right, then this side here is b minus a, and this length here is 2 pi times L. Yeah? Yeah? Can you see that? Is that making sense to you? Formula, which is 2 pi L, which is the circumference, times b minus a, will actually be the surface area of this cylinder. Yeah? That's meaningful. Yeah? Cool. All right, so that's the very simplest thing we can do. Yeah? Now we're going to use this thing that we've understood to try and figure out a more general case. Yeah? And then we're going to do the same strategy as previously. So we're going to take our general function f, like this, and we are going to cut up the base from a to b into equal size intervals. So, as I said last time, if you become familiar with this stuff becomes easy. So I'm going to keep doing this. I'm going to do this many, many times. I'm never going to give you a formula where I don't explain it, and I'm always going to explain it this way. This is the way. This is the way. This is the reason it's true. So the sooner you get into this and understand it and feel comfortable with it, the more meaningful this will be. So if the first explanation on Monday wasn't clear to you for the arc length, just spend time with it. Just spend time with it, and then it will do, and then this will be meaningful. So yeah, just don't check out on this part. Just invest some time into following these arguments. Watch the video again, and then even though this might not be what you're used to hearing about in a math class, I promise you, you're all very smart people. This will make sense to you. This will fall into place, and all these formulas will seem worthwhile. Will have some meaning. Okay, let's do it. So we cut this up into equal size pieces. So we say let delta of x equal b minus a over n, where n is something we decide on later. We let x0 be the first guy, this guy, x0. We let xi plus 1 equal xi plus delta of x, yeah, just as before. So then we have x1, x2, and so on, and this thing is xn. And then we just take an arbitrary piece of this. So let's say we take, this is xk, and this is xk plus 1, running out of space. This here is xk plus 1, but that's the same as just xk plus delta of x, because every time we move from xk to xk plus 1, we just move along by delta of x. So xk plus delta of x, okay? We're going to consider this particular strip like this. Okay, and let's make the graph a bit more interesting on this part. Okay, so that thing here, this is the strip that we're interested in. That's the one we're going to try and figure out the surface area from rotating just that strip. Yeah? So visualize a thin strip. Right? We cut off a thin strip and we're trying to figure out the surface area of this. Yeah? Okay, so what do we see here? We see that the radius of the strip is basically given by this thing here. Right? That's the radius of the strip, right? Yeah? And then what is the thickness? The thickness is given by this thing here. Yeah? And notice that there's an angle here. Yeah? It's not flat. If it was flat, then the thickness would be clear, right? It would just be delta of x. Yeah? But it's not. There's an angle. Yeah? If we had a very steep angle, then it would be a lot bigger than delta of x. If the angle was very, very small, it would be like delta of x. Do you see what I mean? Yeah, so we have to take account of this slope here. We have to take account of this slope. So we're going to take our magnifying microscope. That's a stupid thing to say, of course, the microscope is magnifying. We take our microscope and we blow up this ball and then we put it here. So this is your microscope blowing up whatever you see in this blue ball onto a bigger scale. And then what do we have? We have strip comes up like this. Yeah. The function looks like this. Yeah. And this distance right here is what we're trying to estimate. Yeah. Yeah. Because that will be the thickness of the strip. So when I cut this out, yeah, and then I unwrap it, then the thickness of the strip is this thing. Yeah? Yeah? So, what's that related to? It's related to the slope I have here, which is, of course, related to the gradient. And if we think a little bit more about it, then what do we actually have? This here is thickness, or this is size delta of x. Is this blue visible for you, or is it a bit dark? It's okay? Okay, good. So we have this side of this triangle is delta of x. And then we have to ask ourselves, what is this side? Yeah, what is this side? And it's related to the slope, right? So right here, underneath here, this is the point xk, right? So here, the function has its derivative f prime at xk. Yeah? That's the slope. Yeah? So just as before, understanding the graph by its tangent line, so if we imagine the tangent line like this is the tangent line, it's almost exactly the same thing as the graph. There's a tiny, tiny error, which is way, way smaller than delta of x. Yeah? So if it actually was the tangent line, then we'd know exactly the slope. Yeah? And that would mean that this side here would be f prime of xk times delta of x. Just as before. Just as when we talked about arc length. Yeah, exactly the same argument. Which means that this length here, the hypotenuse, is delta of x 1 plus f prime of xk. That's what this thickness, that's what this width here is. It's just the same argument as before. It's just Pythagoras. Okay. Are you with me, people? Excellent. Cool. So we have all the ingredients, right? So we have this, let me draw it here. We have this thin strip like this. And then this side has got length f of xk. This width right here is delta x square root of 1 plus f prime of xk squared. Well, I forgot to write the square. Pythagoras. Like this. Yeah. And then if we unwrap it, so this is, try to imagine this where we have a, I can't really do it, but we have, so this, where I've done it here, it looks like it's flat on the top. So try and imagine it with not being flat on the top. But we take this thing, which is this kind of cylindrical shape here, cylindrical strip, and we unwrap it, right? And then this thickness here corresponds to this. And then this length here corresponds to unwrapping this circular base thing, right? And it'll just be 2 pi times f of xk. Yeah? So that the surface area created from this strip, so if I did a side view, it would like go all the way down like this, like this, like this. That's the side view of the strip. Yeah? And then the surface area of this thing here, so surface area, can't spell surface, of the strip is what? It's going to be just this thickness, delta of x square root of 1 plus f prime of xk squared. Okay, and then that's this thickness, and then times the circumference times 2 pi f of xk. Yeah? And that answer is fairly precise. The only error is that this thing here is not quite the length because we've approximated this thing by its tangent plane. And the circumference isn't quite given by this because it's a little bit longer when you consider the circumference on this other side. But these are tiny errors. These are tiny errors compared to the size of this. So we can safely just take this to be the area of the strip. So I should say it's equal, it's approximately equal to, but it's approximately equal to with such small errors that we can ignore the errors. And then we've cut this up, or we're going to cut this up into lots of different strips, into n of them, right? So we do the strip here, we do the strip here, we do the strip here, and so on, right? And then we just sum them all together. So if we sum up all the strips, there are n of them. So we start with I equals 1, no, I equals 0. Let's take the right endpoint. So we did it from, sorry, the left endpoint, we took it from the left. So I equals 0 up to n minus 1. Yeah. And then each one of these expressions, delta x square root of 1 plus f prime of xi squared times 2 pi f of xi. Yeah? That is very close to the entire surface area of this rotated graph here because the entire surface area is like the surface area of each individual strip, and each individual strip is very close to this expression. So we add them all together, and it's basically this. So I should say this as a sentence is approximately surface area of revolution. Yeah? Are you with me? Cool. All right, so the yin and yang of calculus. We can figure out something on a very small scale by the fact that it's differentiable. Differentiability means you can replace something by its tangent line, which is linear, which is what we used here. And then the yang is that we can add up very, very small things. Yeah? Because with this new notion of addition called integration, yeah, we can add up actually infinitesimally small things in a meaningful way. Yeah? Yeah? To actually pass from a finite sum, this is a finite sum, to an integral. Yeah? So we're going to go from this expression, which is a finite sum, to an integral by letting n go to infinity. Tell me what the integral of this thing is when we pass infinity. Let's have someone who hasn't spoken before. What is this thing tending to? Let's call this thing star. Think about how we did this last time. So, limit as n goes to infinity of star is what? Yeah, it'll actually be completely accurate. It'll be a completely perfect answer because the tiny errors we have from this and from the fact that the circumference isn't exactly equal to 2 pi f of xi, those errors just vanish as we let the thickness go down to 0. Yeah, because the graph is more and more like its tangent line as we take a smaller and smaller scale. So indeed, this will give us not just an approximate answer, but a perfect answer. Perfect answer. But what is that answer? We want to build stuff. We want to build the world. We imagine we are 17th, 18th century scientists. We need to be able to calculate things, to find explicit answers. Yeah? And we can do this via this tool if we can get an integral out from this expression. So, how did we do this before? Yeah, we did it with Riemann sums, right? So recall how you need to think about Riemann sums, right? We have a function g, and we cut up into rectangles like this to get some idea of the area underneath the graph, right? That is how we introduce Riemann sums to you. Yeah? So then you have an expression like this. The sum k is equal to 0 to n minus 1 if we're doing the left endpoint approximation, where the height is defined by the left point of the interval, g of xk, yeah? And then the base is just the delta of x that we cut things up into. And then your picture says that as we do this, this thing tends to the integral from a to b. This is what you should have in your mind. This is, again, what I mean by this is a language that describes pictures. When you see this, I want you to have in your mind a bunch of rectangles. That's what this thing describes, or the areas of a bunch of rectangles that live underneath the graph of a function g. And you can see from this picture that as we let the thickness of the base tend to 0, this tends to the area underneath the graph. So this is just true from this picture. You can see it. Not a fact to be memorized, just a true thing you can see. Yeah? Are you with me? Cool. Apply this understanding to that. Come on. You can do this. Perfect. Thank you very much. Yeah, and all this guy did was he went, okay, well, in this case, our function g is all of this stuff. All of this stuff, yeah? So in this case, our g, let's put it over here. So g is this, square root of 1 plus f prime of x squared 2 pi f of x, right? If we let g be this, then this stuff in the brackets is just g of xi. So what do we have? We have that if we let g be this, then this thing is just exactly this expression. Yeah? Cool. So then the fact that we know this thing tends to this means that we see this thing tends to this integral. It's not a hard thing. It's not a hard thing. And it's a thing we'll do over and over again. So if this isn't completely clear to you, just spend some time with it. Spend some time with it. Unless you have a very strong background, you have very good luck of being very well prepared, very good high schools, very good whatever, AP, calculus courses, this won't slot into place for you on the first go. It certainly wouldn't have done so, and it didn't do so for me when I first heard it. So one of the things you're going to have to learn is to spend some time looking at things that don't initially make full sense to you, and have some perseverance and just think about it and play it over in your head. In this case, you can even play over the video, and you'll find that every time you do it will make more sense until it does. Don't expect it to go in one shot, and don't give up if it doesn't go in one shot. If you aim for the kind of understanding I'm trying to motivate you to get to for maths, then you're going to have to do this. But you will find that after a little bit of thinking and repetition, it will actually work for you. Okay? Cool. So we have that this is true. So this thing is the exact answer. This is the exact answer. We have the exact surface of revolution. Yeah? Cool. So let's look at this. Yeah? This part right here is from the perimeter. It's from the perimeter of each of these bands. Yeah? Or I should say the circumference, same thing. Yeah? And this part right here is to do with the thickness of the band. Yeah? So this is not a mysterious thing. This is not some magical thing some genius figured out and you'll never be able to follow the reasoning. This is simple. It's just from pictures. Everything is pictures here. There is nothing hard here. No, this is just pictures. Cool. All right. With this formula, we can calculate stuff. Let's do some of that. We're going to rotate y of x, which is equal to the square root of 4 minus x squared, between the range -1 less than x less than 1 around the x-axis. Okay. Yes, that's 4. There we go. So, we draw a picture. So, we're doing this between -1 and 1. So let's put -1 here. This is 1 here. When we are at 0, it's just going to be 2. So, kind of, well, tell me what this thing looks like. What is this graph? Where do you recognize this? It's a circle. Good. So this is part of a circle. Yeah? This is part of a circle. Draw an arrow to indicate around which axis you're rotating, around the x-axis. So imagine you are a manufacturer of soccer balls and you have this like central strip of the soccer ball, which is a different color plastic, different type of leather or something than the rest. And you want to find what's the surface area so that you can know how much plastic, leather, whatever you need to buy in order to manufacture 10,000 soccer balls, right? This is a real thing you might want to do in some situations, right? So we've got this. Let's write down the formula that we know provides this, right? So we're going to integrate from -1 to 1. It's actually symmetrical. We could integrate from twice of 0 to 1, but let's do -1 to 1. Yeah. And then what is the thing? We do the circumference, so it's going to be 2 pi y of x, and then the thickness, which is 1 plus y prime of x squared dx. That's the general formula. Yeah? That's what we learned. So we start off like that, and then we calculate the pieces, right? So we need to know what y prime is. Y prime of x equals 1/2, 4 minus x squared, to the -1/2, and then we differentiate the inner thing, we have -2x. So what's this? This is minus x over the square root of 4 minus x squared. Yeah? And then let's calculate this piece right here. Let's calculate this piece right here. So, let's just write 1 plus, first of all. So 1 plus y prime of x squared. What do we have? We have 1 plus x squared over 4 minus x squared. Let's write the 1 as 4 minus x squared over 4 minus x squared. So let's put it down here. 4 minus x squared, and then plus x squared over 4 minus x squared. So I just put things on the common denominator. Yeah? And then that's just becoming 4 over 4 minus x squared. Yeah? Everybody happy? So then this square root, so let's put things all together. So let's take out the 2 pi, and we have -1 to 1. Let's put in our function y, which is right here. So it's the square root of 4 minus x squared. And then it's this thing, right? Then it's the square root of this thing we just calculated. So it's going to be 2 over the square root of 4 minus x squared. Yeah, just taking the square root of this thing. Everybody with me? Yeah. And what's this? We're going to respect to dx. And then we have this very convenient cancellation. This cancels with this. So then this is just the integral from -1 and 1 of 2, right? So that's just 2 times 2, which is 4, and then times 2 like this. So it's going to be 8 times pi. Okay, cool. All right. So when we have the formula It is just an integration. It's something we already know how to do. It's just something we practice. Yeah? Cool. All right. Now I'll tell you the other formula when we rotate around the y-axis, but we don't do it by changing the function to a function from the y-axis. So this is what I mean. So suppose we have some function like this. Okay? And we want to rotate this time around the y-axis, like this. We rotate around the y-axis. Yeah? Now, we could try and write this as a function from the y-axis and then use the same formula, right? But sometimes it's more convenient not to do that. Yeah? But we still want to get a formula. And we can actually do it. And it's a very similar procedure. So this time I'm not going to go into full details. I'm just going to give you some hint. The procedure is always the same. We cut things up into little pieces. So we've cut things up into some little strip, say xk to xk plus 1, right? So we consider this strip like this. Yeah? But now, this little piece here is not rotated around the x-axis, it's rotated around the y. So we have a strip which is looking like this, rotated around the y-axis. Yeah? Can you see what I mean? Yeah? So then, what's the perimeter, or what's the circumference of this strip? The circumference will be more or less 2 pi times xk. Yeah? Because this is like the radius of the base. Do you see what I mean? So let's write this. So, surface area of the strip yeah, rotate around like this, then the radius is like xk. So I have my piece of paper. This is the strip. So this is not long enough. But this is the strip, right? It's like this. So we unwrap it, right? Yeah. And the radius of the strip we create will be this thing here. Do you see what I mean? Give me a thumbs up if you do. Okay, cool. So that's the radius, and then this thing here is the thickness. You know? This thing here is the thickness. But that thickness we can understand from the formula that we had before by just using the tangent line to approximate this thing as the hypotenuse of a triangle. So then the surface area of this strip will be like 2 pi times xk, you know? And then the square root of 1 plus f prime of xk squared times delta of x. That'll be the thickness of this strip. Oh, sorry, that'll be the surface area of this strip. And this part here is the thickness of it. So this part here is the circumference, and this part's the thickness. Okay. So this will be, this will be hard for many of you to see in one go at this particular moment. You might have some kind of feeling that it makes sense, but having a real clear feeling that this is exactly the right thing probably won't be there, but it will be if you think about it and you watch the previous explanation how we got the other formula. Huh? So this is one of the strips that we want, but we have all of these strips as we cut it across from A to B. So it's exactly the same as before. We're going to have a sum from k is equal to 0 to n minus 1 of each one of these expressions. So 2 pi xk square root of 1 plus f prime of xk squared times delta x. And then we're going to pass to the limit, and it's going to be the integral from a to b. Yeah? And what's this thing? It's just going to be 2 pi x, and then this thing is 1 plus f prime of xk squared dx. So this looks a lot like the previous formula, but it means a completely different thing. Yeah, it means a completely different thing. So if you don't know what this means and you're memorizing stuff, then it seems kind of mysterious how this thing, which looks a lot like the previous thing, means something completely different. If we rotate around the y-axis, sorry, if we rotate around the x-axis, like I'm doing now, we get a completely different answer than when we rotate around the y-axis. We get a completely different answer. I mean, just consider the special case of when we have a constant function. When we have a constant function whose height is L, right, and we go from A to B, yeah, then what do we get when we rotate around the x-axis? Let's put this separately. So, constant function around x-axis. This is what you people already told me. It is just going to be b minus a times 2 pi l. Yeah, 2 pi l is the circumference of the base, and the length is this. Yeah. Now let's rotate the same thing, constant function L around the y-axis. All right, so imagine rotating this constant function around the y-axis. What kind of shape would that give? What would that look like? Perfect, it would look like a washer. It would look like a washer, right? Let's put it over here. It would look like a washer whose outer radius was this thing, B, and whose inner radius was A, right? So this is B and this is A. This is what we would see from rotating around the y-axis. Do you see what I mean, people? Yeah? Cool. So what would we expect the area of this thing to be? What would we expect the area of this washer to be? We've done this before when we were talking about volumes by cylindrical shells. So what is this area? What's the area of the outer circle? Perfect. It's the area of the outer circle minus the area of the inner circle. Yeah? That's what the answer should be. Okay, thank you, thank you. So, we would expect this thing, put it over here, area is pi times b squared minus a squared. So if our formula is correct, when we rotate this thing around the y-axis, that's the answer we should get. Yeah? Which is a completely different answer than this. It doesn't involve L, right? And it's just completely different. So let's see. This is the formula we deduced. Yeah? This is the formula we deduced. So if we apply this formula, so we integrate from A to B, f prime is 0, right? Because it's a constant function. So this whole thing is 1. Yeah? So then this is just 2 pi times x dx. We pull out the 2 pi, we integrate x, it's x squared over 2, b, a, x squared over 2. And indeed, it gives us exactly what we want. It's pi of b squared minus a squared. Yeah? So we have the correct thing. This formula gives us what we expect. And it's a completely different answer. It's a completely different answer because it's calculating a completely different thing. But I claim that the fact that this is the right formula is straightforward from the pictures if you're prepared to invest 20, 30 minutes looking at this explanation, drawing the pictures for yourself. How are we for time? We have 5 minutes. Okay. So I'm going to raise the board and we're going to do some example where we calculate something around the y-axis by using this formula. And then we can also calculate around the x-axis to make sure we get the same answer. And then we'll wrap it up. And otherwise stay. So this is our function. Y of x is equal to x squared from 1, 1 to 2, 4. This is the thing which I mistakenly did before. So rotate around the y-axis. Okay, we draw the picture. We start off at 1, 1. Here we are at 2, 4. Looks like this. Okay, this is 1, and this is 2. Yeah, this is 1, and this up here is 4. Okay, whatever. This is 2, 4. 1, 1. And we're rotating around the y-axis. So we draw a picture, or we draw an arrow, indicate which way we're doing this. So please do this step. It's very easy to forget which way you're rotating around and just calculate the wrong thing. Okay, so now that we have this, it's just using the formula. Yeah? So what's the formula? So we're going to integrate with respect to x. Yeah? Even though we're rotating around the y, this formula allows us to integrate with respect to x. So we integrate between 1 and 2. Yeah? And then the perimeter of these thin strips is given by 2 pi times x. And then the thickness is given by 1 plus, in this case, y prime squared dx. That is what we're doing. Yeah? That's the formula. One of the key things to get right is to get the right formula, right? So even with the cheat sheet, even writing these things down, the fact that this is the correct thing hopefully will be clear from the pictures, from the explanation we gave. Because it seems kind of strange that we're integrating with respect to x to get something rotating around the y, but we are. Okay, cool. So then we just need to find out the pieces, right? So we just differentiate this thing. So y prime of x is equal to 2x. It's easy enough. So then put that in. So let's take out the 2 pi, integral between 1 and 2, x, the square root of 1 plus 4x dx. 4x squared dx. Yeah? Cool. And then this is an easy use up, right? We let u be 1 plus 4x squared. Du is equal to 8x dx. Yeah. So let us write du over 8 is equal to x dx. And then let's do this integral. So it's 2 pi. When x is equal to 1, then we're going to have 1 plus 4, so it's going to be 5. So it's integral 5. When x is equal to 2, we have 4 times 4, which is 16, plus 1, so it's 17 right here. And this x dx is now replaced by du over 8, so let's put the over 8 here. And then we just have the square root of u, like this. Yeah? And then this is just the integral, right? So this is going to be pi over 4. And then, the antiderivative of this is 17. This is 5. And we're going to have u to the 3 over 2, 2 over 3. Let's pull out some numbers. So put this across. So we have pi over 2, and then it's over 3. So it's pi over 6, like this. And then we just put the numbers in. So it's 17 to the 3 over 2 minus 5 to the 3 over 2. Like this. And that's the right answer. Everybody happy? Cool. Now, there'll be instances where you'll have some function where you're meant to rotate around the y-axis, but it's not easy to write it as a function from the y-axis. In fact, we can make it almost impossible. That's the point of this shell method. If you remember the method of calculating volumes by shells, right? It was because we can't always easily write a function from the y-axis. Yeah? So in this case, we can, though. We can write this function from the y-axis. We can solve x to be blah, 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 something in terms of y, right? So second way. So we can do it the second way and then check it. We get the same answer. If you're doing a free response and you have time, this would be a very good thing to do just to make sure you haven't made a mistake, right? So if we think about this function as a function from the y-axis, we write x of y, then it's going to be x of y is equal to the square root of y. Yeah? Because that's what gives this equation, right? Yeah? Give me a thumbs up if you're with me. Okay, cool. So this is our function of the y-axis. And then using the previous formula, so if we rotate around this way and then we integrate with respect to this, then we're thinking about our thin strips like this, right? So then the perimeter is given by 2 pi times this function, right? And then the thickness is given in terms of this function. So then we're integrating from here to here. So we're going from 1 to 4, right? And then it's 2 pi times the perimeter, x of y, right? And then the square root of 1 plus x prime of y squared dy. That is our old formula now applied to this function rotating around the y-axis. This, again, is the thickness of the strip, and this is the perimeter of the strip. Does that seem reasonable to you? Good. Then we just do this calculation. So we have 1 over 2, y to the minus 1 over 2, which is 1 over 2 square root of y, like this. So then this thing, let's call this star. So star is equal to the integral from 1 to 4, and we're going to put 2, this thing, square root of, this is just the square root of y, and then this thing is the square root of 1 plus 1 over 4y, like this, dy. Yeah? And then we just calculate this. So I want to make a common denominator, and I see there's going to be some simplifications. So let's do that. So let's pull out the 2 pi, integral between 1 and 4, square root of y. Let's put this under the common denominator of 4y. So we're going to have 4y plus 1 over 4y, common denominator, right? And then I'm going to take the square root of the top and the bottom, and then I'm just going to have a 2 at the bottom. So then it's just going to be, so this 2 will cancel this. It's going to be pi into between 1 to 4. And the square roots will also be killed. So we're just going to have the square root of 4y plus 1 dy. Yeah? Just taking the square root of the bottom. Yeah? So on the bottom, I'm just going to have 2 square root of y. This 2 will cancel this one, and the square root of y will cancel this, so we just end up with this. Are you with me? Yeah? Cool. And then what's this? This is now another easy candidate for u sub. We put the stuff inside the square root is just a linear function, so we let that be u. So then u is equal to 4y plus 1 du by dy is equal to 4, and therefore dy equals du over 4, and then we just call this thing star. So star is equal, we've already called it star, there's no need to do it twice. Star is equal to pi. We change the limits, so when y is equal to 1, then we just have 5. And then when y is equal to 4, we have 4 times 4, 16, 17. And this is our guy, so it's square root of y. And the dy became du over 4, so let's put the over 4 right here. Du, so it's pi over 4. And then 17 over 5, y to the 3 over 2, 2 over 3, and we get the same thing, right? So then the 4, so the 2 over 4 is 2, and then this 3 goes along, so it's going to be pi over 6. And then it is 17 to the 3 over 2 minus 5 to the 3 over 2, which is exactly what we had before. Yeah? So this thing, call it star star, is equal to this. And we're happy. We have exactly the same answer from 2 different formulas. We must have got the right answer, and we believe that these formulas give a meaningful thing, give us the quantity that we want. Cool. Cool. All right. Are you happy with this? Yeah. Okay. So let's wrap it up for today. I have office hour now, so stick around if you have any final questions or any further questions or any questions about anything previously that we've talked about. Otherwise, I will see you all on Friday. Have a great day.